In the last lecture, we have seen one methodology called multi-cycle approach to design the process. So in that approach, the primary goal is that to reduce the clock period. So clock is drive the entire processor, and we want to minimize the period of that clock, or another way to say, we are trying to improve the or increase the clock frequency so that it can process more data, right? Or process more instances. And it has also other two secondary objectives such as resource minimization, resource utilization minimization, and the common case analysis. Here in this common case analysis, we want to give exact amount of time to each instruction for their execution. Okay, and so what was the goal of in that approach? So if you remember this one, so here you can see, okay, here we are in this D flip-flop, we are sending the input to the combinational logic. That means some processing component, right? And after the processing, it is storing the output. And these two D flip-flop is driven by a clock. So using this principle, we want to find the, using this principle, we find the clock period. Here in this case, it's a T. Okay, and we want to minimize this T. So what we did, we split this combinational logic into two parts, and we assume that each part takes equal amount of time. So, and we put D flip-flop in between them. So here you can see. And then what we did, like first we take the input in this D flip-flop and we send that input to the combinational logic, and then we lock this D flip-flop. And in the next time, after processing the sum, after processing the that input, we are sending the output to this D flip-flop. So that time we'll enable this D flip-flop. Okay, and after that we'll send this output into this combinational logic, and then after a few amount of time we'll store the output in this D flip-flop. So when we are storing the output in this D flip-flop, at the same time we are taking next input to this D flip-flop, and we are enabling this D flip-flop. So next data would come here. At the same time, the previous data's output would come out here. Okay. So in that way, and we have seen how to calculate the clock period for this purpose. So if you remember the timing calculation, so every time we have to find out the delay between source and destination pair. So here, this is the first source, this is the first destination, and the next time this is the second source, and this is the second destination. Now, after designing this data path or this data path processing part, so you can see the clock period is improved here. So it is reduced by 2, and you can see frequency has been improved by 2. Okay, so in this way, we can improve this processing time. So this is the general principle, and we applied this principle to design the multi-cycle based MIPS processor. And what we did next time, and also remember, this is not the pipeline one. Okay, why it is not pipeline one? Because if you, in the pipeline data path, so there would be continuous flow of this input to the data path, right? However, in the structure. So, and this is the general principle to minimize the clock period for any kind of digital design. So now we, next what we did previously, we applied this general principle to design the multi-cycle MIPS processor. So what we did, so we have taken individual instruction, and then we draw the data path, right? And also design the data path, we have removed the redundant resources such as data memory, right, that we had in the single cycle one, and also we had removed the additional adders, right? So, okay, so if you remember, this is the page stage, okay, and then you can see here, this is the LW's data path. Here we are inserting the non-architectural element such as IR, MDR, okay, and E, right? So in this way, if you remember that, that approach that we have discussed for general approach to design the multi-cycle data path. So here you see that is the, like, this is the fast flip-flop. The output is coming out, right, from this, and then we are reading the instruction here, and then you can think this is the second flip-flop, this one and this one, right? And we are storing the instruction here, or another way to say it, we are storing the output here, and then you can see we are giving these to the other processing unit. Okay, and after that you can see we have storing that one, that result in the temporary, or non-architectural element such as A. Similarly, here you can see we have another non-architectural element called LU out. So in this way, the entire delay for LW instruction has been splitted into 5 parts. You can see. Okay. So same way, we have also drawn the data path for SW. Okay. Similarly, we have drawn the data path for R type instruction. So now today we will draw the, or we will design the data path for BQ instruction or branch type instruction. So these instructions are, like conditional jump, you can say. So what is the meaning of this instruction? So here, if the content of this register S1 and S2, if they are same, then the PC would be loaded with the offset, the branch address. Okay, and this is the format that we have. And here you can see offset is the 16-bit, and this offset, okay, this offset is nothing but telling about number of instructions. Okay, so meaning that PC has to be jumped to this particular instruction if the condition is true. Okay, so and we'll perform this operation into 3 different steps that you can see here. Okay, first we'll read the okay, so here you can see first we'll read the instruction into the IR. So actually this would be IR, okay, and memory and PC. At the same time, we increment the PC by 4. So first we'll load the instruction to IR, and the same time we'll add the PC plus 4. The next step, we'll calculate the uh, branch address, okay, and we'll store it into the other non-architectural element or ALU out. And the next step, we'll perform the comparison, okay. And if it is true, then we'll load the PC with the branch address, calculated branch address, which has been stored in this non-architectural element called ALU out. Okay, so let us draw the data path for that. Okay, so we have to first fetch the instruction, and to fetch the instruction, or maybe we have to fetch the instruction first, and for that purpose, so PC holds the instructions address, and the instruction is stored in the memory. So we have to bring the PC's content to this memory, and then we have the memory read signal. Now, if we make this signal 1, then the instruction would be come out from this. And then, if you remember, we are storing that instruction in the IR register. Okay. Now, after that, if you remember, we are adding. So we have to also calculate the PC plus 4, and we are doing that PC plus 4 using the ALU. Okay. This is our ALU. So to perform the PC plus 4, from PC plus 4, we have to bring the PC's content into the ALU, and also we have to provide the 4. So now, so this is the one hand of the ALU, and this is the other hand. So this hand will provide 4, and will provide PC. Okay. Okay. And so also, if you remember, we have to enable the IRI to hold the instruction here. Okay. Now, so PC is available here, and then 4 is also available here. So we have to perform PC, we'll perform PC plus 4 here. Okay. Now, you should remember, we won't store PC plus 4 in the temporary or non-architectural element in the such as ALU out. Why? Because if we hold that value also in the ALU out register, then once one clock cycle delay would be increased. And because of that, we are not storing that in the ALU out register. So we are directly giving it to the PC. Okay. So now, okay. And to load that value into the PC, we have PC write signal. Okay. Now this is our ALU. Okay. Now we have to calculate the branch address in the next step. So this one. So to calculate the branch address, we need offset, and offset is 16-bit. So first we have to make the offset as 32-bit, and then if you remember, so this offset tells about number of instruction. Okay, to be jumped. Now, and in each, and as it is a 32-bit processor, so each instruction takes, okay, 32-bit to, the instruction format here also 32-bit. Now, the memory that we have here, so this is the byte addressable memory. So in that way, each instruction will take 4 consecutive location to store it. And because of that, after performing the sign extension of the offset, we have to multiply that value with 4. Why 4? Because each instruction takes 4 consecutive byte, okay, to store in the memory. Okay. So now, let's say we have sign extension unit here. So instruction has been stored here. Now, let's say we'll read that offset here, and we'll perform the sign extension, and then we have to multiply that value by 4. And in hardware, we can do such thing using left shift by 2. Okay. Right. So it is available here. Now we have to add, right? So PC, if you here PC holds the PC plus 4. Okay. So now we have to bring that PC plus 4 here, and we have to provide that offset using this path. Now you can see here, ALU is getting, ALU's 2 hand is upper hand and lower hand. Both are getting the value from 2 different sources. Now, if you remember, if a port gets the data from 2 different sources, so we have to put the multiplexer. So we have to put multiplexer here and here. So now we'll put the multiplexer. Now, if you remember, if we design multiplexer or insert multiplexer, we always have to specify the input levels, right? Because otherwise it would be very ambiguous scenario if we don't mention these values. So you have to always remember that. So now through this path, PC and PC plus 4 will come. Okay. And through this path, we'll get, it's the first time 4, and next time we'll get here this one. Okay. Now here, okay. So here, presently you can see it is receiving, PC sometime here in the first phase we will receive PC, and then next cycle we will receive PC plus 4. Okay. So this path, I have made mistake. So actually this path is receiving input for this time, for stage 1 and stage 2, it is receiving only from 1. But we'll see when we calculate the this third step, right? we have to bring the register content also. So that time this marks, this hand would be would be connected. So for the timing, it is like this. Okay. Okay, but yeah. So now we have to specify the select input of this box. Let's say this is ALU SRCA, and let's say this is B. Okay. Now also, I mean, we have to provide the ALU control, and so this ALU control would be there when we have also calculated PC plus 4. Okay, so this is the ALU decoder. Okay, so it will take the value from ALU off, and also the func field would come, right? So func field would come from the instruction, right, that we have discussed for the R-type instruction, right? So now it has performed this PC plus 4, and also it has calculated this branch address. Now we have to store that branch address into the non-architectural element, this ALU out. Okay. So we have the branch address here. Okay. Now in the next step, we have to perform the comparison. Okay. Now to perform the comparison, we have to bring the RS register content and RT registers content into the ALU, and we'll perform the comparison. Now we need a register file here. Okay. So let's say we have the register file here. Okay. Now, so RS value would come via this address, and RT would come via this. And actually, we have very minimum amount of space. So then we'll have the A register right here. So that value would be stored in A register, and the other value would be stored in the B register. This is A, and this is B. Now this time, now you can see we will connect this A content with this. Okay. Now you see here in this case, we have to provide the B to these marks, right? This is A register and this is B register. We have to provide this to ALU. Now you can see we need here in this hand, right? Another marks, right? Or marks size or dimension can be increased. So let's say if we provide that value here, and right, so provide here, and we'll make that one as, let's say, 2, right? I mean, because of that space, I mean, okay. So these 2 would be inside marks, right? And then this time the select input, I mean, would be 2-bit. Okay. So now we have calculated the, we have performed the comparison. Now, if you remember, we have 0 flag here. If this value is true, I mean, both the value is same, then this line will be activated. Okay. Now, see, this is like here we are performing the subtraction to compare the 2 values. Now, if if 2 value is same and we are performing only subtraction, like here the instruction is BQ, right? But let's say we have sub instruction, and sub instruction, it will subtract 2 register value and it will store into the register file. So if both the values for here in this case R1 and R2, let's say, and we are storing it R3. Now if value of R1 and R2 are same, that time also this 0 flag would be activated. Okay, so that means this 0 flag can be activated for more than one instruction. Now we have to tell, okay, we want 0 flag when this is a BQ statement or BQ instruction or branch instruction. So because of that, we have to perform the, like, it is so if you remember logically, if this is a BQ state instruction and 0 flag is 1, then we'll load. And to perform that operation, we need, and if you remember, that we did also for single cycle. So 0, and then we have to tell we need this value only for, let's say, branch instruction. Okay, now it is ready. Got it? Now, so this is the branch address. Here it is available. Now we want to load this value onto the PC. Now here you can see, so this PC write would be 1 when we want to load the PC with PC plus 4, right? So that is one condition. Similarly, when the branch is 2, the branch condition is true, then also we load the PC with new value. So that means we load this PC for either PC plus 4 operation or the branch address. So you see, we have OR thing here. And because of that, as we have OR, so we need OR gate. So it will be like this. So first, let us erase this. And then, so to input OR gate, and let's say this is PC light. And how about the other input? So other input would be our this branch condition. Okay. Now we have to provide the address, branch address here. Now you see, this port is getting value from 2 different sources. So which component do we need here? Multiplexer. So we have to insert the multiplexer here. And the branch address would come now. Okay. Now we need select input is PC source. Okay. If it is 0, then we load the PC with PC plus 4 through this path. If it is 1, then we load the PC with branch address. Okay. Now we'll discuss the other instruction, that is add. So add means, like here we have add E and destination and this source, and then some value we have here, let's say 50. So meaning that we load R1 with the addition of R2 and the offset, that is 50. Okay. Now, so we'll perform this operation into 4 number of steps. So first step is this one. I think this is common for all instruction. We load the instruction in the higher register, and then we'll increment the PC by 4. Then we are reading the value, that is R2, that is RS, right, into the A register, and then we are performing the addition A with the immediate value. Okay, and then we are storing into the non-architectural element LU out, and then we are writing that value into the register 5, because we have to write that value into the R1. So let us see. So first we have to fetch the instruction. Now to fetch the instruction, we have to bring the PC's content into the data memory, or memory. Okay, so this is the address. This is memory address port, and we have register here, that is IR register. Okay, and we have this IR write signal, and also here we have mem read signal. Okay, now we have fetched the instruction. The instruction has been stored here. Now at the same time, we want to perform PC plus 4. So to do that, right, we have to give 4 here, right, and we have to bring the PC's content here, Now to bring the PC's content is available here. So this is ALU. We have to provide ALU control through ALU decoder, and it is taking input ALU off. This ALU off would come from the controller. We will see. And also, I mean, for R type instruction, remember you have to provide func field. Func field would come from the this instruction. I'm not drawing that one because it would be hazy or it would be messed up here in this drawing. So because of that, let's say that is the func field. So it will come from this instruction. Okay. Now we have performed the PC plus 4. Now we have to load that value in the PC. So if you remember last time also we discussed that PC plus 4 won't be stored in the ALU out register. And we have PC write here. Okay. Now in the next step, we have to read the register from the register file. All right. So we have to provide this address, right, register address, that is RS, and now we have two register. Let's say we are storing that in the A register. Now we have to provide this value in the ALU, and also we have to extend this immediate value. This immediate value is 16 bit. Okay, now we have to make it 32 bit. So let's say this is our extension unit to 32, and this is the value we want to add. Okay, we don't I mean, because as it is a real value, no need to multiply it with 4. You may wonder why are you not doing multiply with 4, because this is the data. Last time it was the instruction, number of instructions, and because of that we have performed the multiplier with 4, right? So now we have to provide this value to here. Now here you can see ALU's two hand, upper and lower, are getting the value from more than one sources. So we have to incorporate or insert the multiplexer. Okay. Now we have multiplexer here and here. Okay. Now we have to tell about the select input. So this is ALU SRC A, and this is ALU SRC B. Now we will store that value, right? That value will come out through this port, that is ALU out result, or let's say, and we have to store that value into the ALU out register. ALU out register. Okay. Now the value is available here. Now we have to write that value onto the register file. Now if we want to write the value onto the register file, we have to provide the register address. Okay. So let's say this is our write address, write register address, and write data. So data would come via this path. Okay. Now we have to provide the address of that register, that is actually RT. Okay. Now we provide that value here, and then we have to provide the write signal. Okay, that is reg write. Okay. Now value will be written here. If you provide it, make it 1. Got it? Now we'll see the other instruction. So here, this is another jump instruction. This is unconditional jump. Okay, so if you remember, this is the format. So we load the PC with new value. Okay. So new value in the sense that so here the address, or you can say number of, not actual address. This is also the number of location to be jumped. Okay. So as it is number of location means, if you remember, we have to, and this is a byte addressable memory, and each instruction and data, right, that would be stored into 4 consecutive locations. And because of that, we have to multiply this one with 4. Okay. So first we have to perform the that multiplication with 4, and you can see the operation, like the first 4 most significant bit of this address, because here address is here 26 bit, right? 26 bit. If we perform left shift by 2 or multiply by 4, then it would be 28 bit. Okay. Now how about the rest of the 4 bit? Now we can see that we are concatenating with the PC plus 4. Okay. And as we have this value, then no need to perform the sign extension, because see 4 bit, right? So 4 bit we are putting into the MSB part, and MSB itself tells about the sign bit, and the PC's most significant bit would tell the sign thing. Got it? So now we have to draw the data path for this instruction. So PC, we have to load the, or we have to read the value from the memory, and we have mem read signal. We load that into the IR, and we have to provide IR write. So instruction is available here. Now see, this is 26 bit. Now we have to multiply that value by 4, and this is that can be done using left shift by 2. Okay, and we have to also perform the PC plus 4. Right now, PC plus 4 is we'll do that PC plus 4 thing using the ALU. Now, so PC would come via this path. Or would come via this path, and we have to provide the ALU control signals to ALU decoder, and we have to provide the ALU off, and the connection is there, or func field. It would be used when you have R-type instruction. Now PC plus 4 is available here. Now we have to load the PC plus 4 in the PC. So you see that is and so this value. Now we have PC write signal. Okay. Now next time, so we have extended, or we have multiplied that offset, right? This offset by 4, that is available here in this board. That value is available here. So here it is 28 bit. Now PC plus 4 is available here. So let's say we have to perform the concatenation. And so what is that concatenation? So the most 4 significant bit of this PC plus 4. So here next time PC plus 4 is available here. Right? Got it. So that value would come here, that 4 bit. So 4 bit, such as, number of bits is 31. Okay, 31, 30. Okay, and 29 and 28. And here the 28 bit would come from 27 to 0. Now we'll concatenate that thing and we have to load that thing in the PC. Now you can see PC's this port is getting value from this ALU and this unit, concatenation unit. So which component do you need to add before the PC's input signal? Right. So we have to put the multiplexer. So we have marks here. Okay. Now, so here 0 for 0 this would be the path, and for 1 this would be the path, and we have the PC source. Okay. So this is the data path for J-type instance. Now what is the next step? Okay. So in this lecture we have considered only as 6 to 7 instructions. Now if we want to design the ISA for MIPS, then we have to draw the data path for all the instructions that we have in the ISA. And then what was the next step? If you remember the single cycle one. So now we have to combine the each instruction data path, right? And what is the step? So we have to combine the for each instruction. And for that, I mean, if you want to combine that, which component do you need to add, right? So we have to insert multiplexer, right? So we'll put the multiplexer before a input port, right? If that port gets the input from the different component. Okay. So for example, you can see here we have incorporated, I mean here this data path is for only 6 to 7 instructions, right? So right, that we have discussed. Now you can see here. So this is the multiplexer. This is also one multiplexer, and this is the one multiplexer. We have this multiplexer and this multiplexer and this. Now let's say if we explain this one. So you can see this multiplexer is just before the PC's input port, right? Now PC is getting the value from 3 different sources. One is our PC plus 4. So PC plus 4 would come via this part, and the branch address would come via this path, I mean after the ALU out. And for jump instruction, right, we just saw the jump instruction. See, the value is coming out from this port and they are coming here. Now here we are performing this thing is, this one is the concatenation part that we have just saw. So this is the concatenation unit, right? So we are performing the concatenation here, and if it is a jump instruction, then it would be 1. At that time, the value would come via this path. Okay. Now, if you remember this this one, right? We had this one, right? So this is the memory, and memory is getting the data or address from PC, right? When we want to fetch the instruction. Next time, I mean, also, I mean, here in this case, we have only one memory. Now, if LW or SW wants to read or write the data from the memory, right? Right? If it wants to read, when the LW wants to read that instruction data, right, from the memory, and SW would write that data into the memory, right? Then you see we have to provide the address from ALU out. This is ALU out. Okay, this part is ALU out. So you see this address is coming, right, via this one. Now this address port is getting the value from 2 different sources, and because of that we have introduced this marks. Similarly here, right? So this is the write register. Right? So write register means, so we have to provide the address of the write register. If it is R type instruction, then we have to provide the RD field. RD would come from 15 to this. If it is LW instruction, then RT would be the, right? So RT would be from 20 to 16, if you remember, right? And now, so write data. So for LW, write data would come from, this is the MDR register, if you remember, via this path. And for art type instruction, right? So data would come from ALU out. Okay. So similarly, here also you can see we have the marks. So this is the strategy. Like when we combine the data path, then we need only the multiplexer, and we insert the multiplexer before a input port, where when that port is getting the value from different sources. Right? So that is the strategy, right? To design the or to combine the data path. Now, after combine the data path, what we have to do? So we have to find out the control signals. So what are the control signals do we have here? So you can see here we have this select line of these marks. This is the memory read and write signal, right? Jump, right? IR write, register destination, right? And mem to reg. So these control signals, right, which are highlighted using blue color. Okay, so that would be generated from the controller. Now we'll see the controller design technique. Okay, so in this way, you see we have identified the 15 control signals, and beside the control signals, if you remember, we have the states. When we say 1, 2, right? So we have here also we have 4 states, right? So that means the states are also the part of the controller design. So in that way, we have these many, 15 control signals and the state. Okay, and how many bits do we need for this state? That we'll see. Okay, so now these are the control signals, right? Now what we have to do next? Now we have to find out the truth table. Okay, so like for example, you see, or if you perform the parallel reasoning with, let's say, 2 input and gate. So let's say we have 2 input and gate. This is, let's say, A and B input, and this is output, let's say O. So if you remember the truth table, we have input and we have output. Right? So these are the possible inputs. So we have the relation like 0, 0, 0, 0, 0, and 1. So now we have to find find out the relation between input and output. So this is input and this is output. Similarly, by same principle, we also should have the truth table. So now for this, right? So if we apply this concept to controller design, you see these would be the truth table, as we have the state in this table. So sometimes it is called the state table or state table. Okay. So what are the inputs? So inputs are nothing but opcode that will come from the controller. Sorry, and that will come from the instruction opcode and the current state, or we are saying it is as present state, P states. Okay. So value can be 0, 1. So we have these 2 input, and then these are the output signals, right? You see these 15 signals, and also you see here we have the next state. So we are telling after performing this operation, go to the other state, and because of that, we have the next state field in the output also. Okay, so we'll see this thing in detail. Okay, so this is the controller, like you can see here, and all these control signals are coming out, and we have connected them here. Okay, so this diagram has been borrowed from the book Computer Organization and Design by Patterson and Hennessy, chapter 4. Okay, so these are the steps involved to design the multi-cycle approach. You can see here we have 5 stages. So instruction phase, here what we are doing, you see most of the time we are loading the instruction from memory to the IR register, and then we are incrementing the PC by 4. And you see next time we are reading the value. Okay, and you see these operation. So these operation we are performing like here we are calculating the branch address. So you may wonder, like, why are you doing this thing in the second stage? Because if it is R type instruction, because all these instruction would go through this. You can see the R type instruction, memory type instruction, branch instruction, jump, right? So all this instruction would go on 1 and 2 stage. So the instruction like for archive instruction, right? This part won't be very useful. Like when if it is a branch instruction, conditional branch instruction, then we'll have the advantage that time. And then you see we have the different operation for archive instruction. Okay, so we have the different operation for memory type instruction, right? So you'll see like all these things in details. So now this is for fetch stage. Now fetch, if you remember, right? So in the fetch stage, what we are doing, we are loading the PC value. I mean, we are loading the instruction in the IR register. Okay, instruction register. Okay. Now and then what we are doing, we are incrementing the PC by 4. Now if you see the data path here, okay. So here, if we want to bring the PC's content into the address field, then you see we have to make this I or D as 0, right? And then we have to make this I write as 1 and also this memory read as 1. Okay. So okay, and then we load this value. Now we want to perform PC plus 4. Now for PC plus 4, you see PC would come via this path. So we have to provide ALU source as 0, right? Then PC is available here. Now 4 would come via this path. So we have to mention here ALU SRC B as 0, 1, right? Now we have to provide ALU off. So this would be 0, 1. So 0, 1, so we'll discuss like when we'll discuss about the ALU decoder, or also we have discussed this thing in the single cycle when we design the single cycle data path. Now you see this func field, right? This is the func field that is coming from the IR register. Okay, and then we'll perform the PC plus 4. So PC plus 4 would be available here, and you remember PC plus 4 is we are not storing the PC plus 4 in the ALU out. So this is ALU out register. Remember, now it is bypassing that register. Now, so we have to provide PC source as 0. Got it? Then value is available. Okay, I mean, and then we have to decide the enable input of the PC. So here, this is, I mean, we are fetching the instruction. So this is not the, I mean, so whatever the instruction, right? So then only PC write would be 1 in that step, and for the remaining step, so I mean, this value would be 0. Okay, right? So, and because in the second step, the decoding would happen, right? Because see, I mean, we just fetch the instruction and we are performing the PC plus 4 that time. So now we can see only PC write is 1 and the rest of the signals are 0. Okay. So now, so in that way, we got this value, right? So IOD is 0, memory read is 1, right? LUSRC A is 0, LUSRC B is 0, 1, PC write is 1, and PC source is 0. So in this way, we can generate the control signals during the first step, and first step is common for all the instructions. Okay, so in this way we can fill this value. If it is fetch state, then we just saw 0, right? And then the jump, right, that is also 0. Memory write 0, memory read because we are reading the instruction, right? So in this way you can fill this table, and this is for, let's say, state 0, right? After filling this value, we can say go to the state 1, right? So we can say state 1. So this thing we'll discuss in this table. You see here. So currently we are in our controller in T0 state. Okay. So it is T0 state. It is activating I or D signal as 0 that we just saw. IR write as 1, memory is 1, right? LUSRC 0, LUSRC B is 0, 1, LU off, sorry. So LU off would be 0, 0. So PC source is 0, 0, PC write is 1, jump is 0. And then you can see we are saying go to the step T1. Okay. So similar way, so in the next step, the next step, what we are doing, we are reading the two value from, right, from the register file, and we are storing them in the A register and B register. And this is coming via RS and RT field. And also we are calculating the branch address here. And for that purpose, what we are doing, like to calculate the branch address, if you remember in the data path, so PC plus 4 would available here, right? PC plus 4, and then branch address would come via this path, right? So in that way, that time this value, right? So this would be 0, and this would be the 1 1, right? And we have to provide the ALU of, and branch address would be calculated and it would be stored in the ALU out. So you can see here, right? You see ALU-SRC is 0, ALU-SRC B is 1 1, and branch address means we are performing addition, so ALU of is 0. And we are performing this operation in the T1 state. And here earlier, you see, we are saying after fetching the instruction, go to the T1 state, right? And here is the T1 state's action. So we are reading the value into the from the register file to the A and B register, and we are calculating the branch address. And to do such operation, we are activating this control signal. And you see in this table and this table also, because we have 15 signals, and here we have less than 15 signal. Here also we have less than 15 signal, right? So the signal which are not included in this table, by default they are 0, or you can say they don't get. So next we are saying, you see in this next field, okay, we have nothing here. I mean, so it is don't get state, because we don't know what is the instruction. So because this is the decoding stage. Now after the decoding stage, okay, the state would be different. If it is R type instruction, then we have this different. So here you can see this is for LW instruction. Okay. So in the LW, right, we are calculating the effective address in the third stage, so T2 stage. So, and to activate, to perform that action, we have to activate these signals like this. And then we are saying, go to the T3 state. I think you can, like, if you go to the data path and you can see like which signal has to be activated during the calculation of the effective address. I hope you got this idea, right? So in this way, we can define the state and the corresponding control signal during that state to be activated, right? And then we are saying go to the this state, next state, right? Now you see after 4th, so here it is saying go to the state 4. Now T4, right? And then in the T4 we are saying to the T0 state. So T0 state, if you remember, that is the fetch state. That means after execution of an instruction, we have to fetch the next instruction, because this is general purpose processor, and general purpose processor job is to fetch, and it is running the fetch and execute algorithm, so it has to fetch the next instruction. Okay. So because of that, we have T0 value in the next. In these ways, you see for each instruction, here we are talking about SW, and we are generating the state and the corresponding control signal. And here you see at the end, we are saying go to the fetch stage to fetch the next instruction. So in this way, this is the table for state table for R type instruction. Okay. The same way we have discussed for fetch and decode, and right. So by same principle, we can assign the control values here for each state. Okay. So this is the state table for branch type instruction, and this is the fetch state. After finishing the execution, we're saying go to the fetch state to fetch the next instruction. So this is the addis instruction, right? And this is the jump instruction. Okay. So this is the state diagram of the controller. So here you see this is the T0 state. So this is the T0 state. This is the T1 state. So in this way, we have, see, so here this is for J instance. Okay. Now you see LW has the longest state. It contains maximum number of states. So T0 to T4. Right? And total number of state here in this case is 10. Now, if you remember this question, so how many bits, right? How many bits do we need to design the controller? I mean, to design the state. So here we have, so 11 actually, starting from 0, right? We have 11 states. Okay. So how many bits do we need for this state? So if you take log base to 11, then so 4 bit. Okay. So we need 4 bit to represent a state. Okay. Now if we see this thing, if we and also by the way, so you see this phase state is the starting state. Okay. Meaning that if we turn on the processor, then the controller state would be this one. So it will start fetching the instruction. Okay. Now in this way for LW you see how many state it is taking. So 1, 2, 3, 4, 5. So we have 5 state for LW. Similarly for let's say add. So we have 1, 2, 3, 4. And to execute each state operation, we need one clock cycle. Right? So in this way, you see, then LW will take 5 clock cycle to finish this execution. For example, this add, it will take 4 clock cycle. Right? Similarly, you see for SW is also taking 4 clock cycle. Right? However, BNE is taking 3 cycle. JA is also taking 3 cycle. So in this way, so for this 6 instruction, we need this many clock cycle to finish this execution. Now for single cycle, if you remember, for single cycle, right? Cycle, right? So LW is taking 1, SW is also taking 1 clock cycle. So all the instruction is taking only 1 clock cycle. Okay. So now seeing this comparison, right? You can say, okay, so you can see, so this is 1, however here it is 5, right? So intuitively, you will say, okay, the speed of this processor is slow, but the clock period, the T would be lesser, right? Let's say this multi-cycle would be lesser than T of single cycle. This is the single cycle. Okay, so that means that processor will process the data very fast, right? And also here, you see each instruction is taking exact amount of clock cycle to finish this execution. In the single cycle one, so if it is R-type instruction, it is taking extra amount of time, and that extra amount of time is decided by the LW, because LW was the or is the slowest instruction in the MIPS ISA. Okay, so that was the disadvantage for single cycle mode, right? Now, okay, so now we'll see the controller. So in the controller, so let's say this is the controller, okay, and here that so we have 15 signals, right? Control signals, and then we have 4 bits for state. This is the state, okay, and this is for that control signals like multiplexers, select line, right? Memory read, right? Control signals. Okay, so total 19 signals we have, right? So these are the output, right? Now you see here the output is coming to the input, right? Input to the controller, you can see the opcode and the state, which is coming from the state register, and you see the connection. Okay, so connections are in here state. So output of the state is coming to the input to the controller via a register. Now, as we have the memory component here, so this is the sequential control unit or finite state control unit. Okay, and this diagram has been borrowed from a book by Patterson Hennessy, and Computer Organization and Design, the chapter Appendix T. Now we'll design the controller. So if you remember, in the single cycle based processor, so we have generated the control signal using 2 different ways. One is the microprogram based approach. So in microprogram based approach, if you remember, so we store the entire truth table, okay, into the memory, and then we fetch the control word or truth values one after another. Okay, and in this multi-cycle one, so that table would be the state table. Okay, so we'll also store the state table in the memory, and then we'll fetch the control word or control values one after another. So that is the memory-based approach. Okay. So other one is, we also have seen, right, for single cycle based processor, the hardware-based control unit. Right? So in that case, so we design the logical expression for each control signals, and then we realize that logical expression using the and OR gate. You remember? Okay. So using the basic gates, we'll design the logical. Using the basic gate, we'll design the logical expression. Okay. So we have these 2 approaches: microprogram based control unit and the hardware based control unit. So we'll see these 2 approaches in detail. So if you remember, right, so now we are discussing the microprogram based control unit. So here, this is the state table that controller has. So if you, I think you can remember like how to populate these values. So these are the output signal that we have seen just now, right? And here this address, so the address is the input. Here actually this is address, or let's say this is the state. Okay. So this states here we represent using the decimal value. So we represent the state as decimal value. Here also we have the state. So we are saying next address or the next state. Okay. So we represent this thing using decimal value so that we can understand quickly. Okay. So now this is our state table. So these are the output, right? And we have here the input, that is the state. Okay. And also we have the output. So we'll see. Okay. Right. So now you see here in the first location, okay, of the memory, we have stored the control word here. Okay, so we are telling, so as we store this thing in the memory, so here we are storing that data that we store in the memory as a control word. Okay, so these are the control word. So similarly, like memory, we have word concept. So here we have the control word. So in the first location, okay, the 0th location, we have stored the control word related to the fetch state. You can see here. Okay. Similarly, in the second location, we have stored the control word related to decode stage. Okay. Now in the third location, okay, we have stored the control word, okay, for LW instruction, and the entire control word has been stored into 3 consecutive locations. So second, third, and fourth. Now in the fourth location, you can see here the next field. Okay, so next field you can see here it is saying the next state. So you see it is written 0 here, meaning that it will start fetching the new instruction. And as we have stored the fetch control word in the location 0, because of that we have stored the 0 here. And this state specifies the end of the LW's execution. Similarly, for SW, we have stored the control word in 2 consecutive locations such as 5 and 6. And you see the next field in the next address or next state field here. Okay, so it is also saying that SW has finished its execution. Now we have to fetch the new instruction. So same way, each instruction, right? You can see here the last step is talking about the fetch. Okay, so in this table, so we have also decoding table. So in the decoding table, you can see here we have the opcode and the address field. So here in the opcode column, you are seeing the LWSW. Actually, it would be the opcode value. Okay, so 6-bit opcode value. And here the address, you can see here we have mentioned the 2. So 2 means the starting location of the LW's control. Similarly, for let's say ADDIE, you can see we have written 9. So we have written the ADDIE's control word at the location 9. So in this way, we have populated this table. Okay, so now in the table, we can see we have the additional signal called mode field. Okay, so here you can see mode fields is a 1-bit value, and most of the cases you can see mode field value is 0. However, for decoding, the mode field value is 1. So what mode field does is that it tells about the source of the next address. So when mode is 0, it is saying that okay, the next address would be coming from the control word itself. When mode field is 1, then it is saying that the address would come from the decoding table. So we'll see. And because of that, you see in this decoding control word, we have don't care state, because after the decoding, controller will know the type of the instruction, and then it will start fetching the control word based on the opcode of that instruction. Okay. So here in this table, we have say actually we have 15 signals, and you see this is 2-bit. So we have 17 bits plus for this mode. Okay, so we have 1 more bit, and for state we have 6 bit. Okay, and we borrowed this concept from these 2 books. So one is Patterson Hennessy, and another one is Hamilton. Okay, so chapter 5, and here it is chapter appendix C. Okay. So here we have stored the entire truth table in the memory, and we'll read those control word based on the address. Okay. So now we'll see the architecture of this microprogram based control unit. So here, as it is a memory, so it is the control memory. So the entire truth table, okay, or state table has been stored here. Now, as it is the memory, then we have to provide the address to read the data, and here data is nothing but our control word. Okay, so this CMR, the control memory address register, would provide the address to this control memory, and then we will read the control word. Okay, and that control word would be available here. Okay, now as we mentioned that sometimes control field holds the next control word's address. So this NA, so that is the next address field. Okay, and you see this is the mode field. It can be 0 and 1. Now, as we mentioned earlier that address of the control memory register can come from two different ways. So one way is that some part of the control bit would provide the next control word address, and other ways is that this decoding table would provide the next instructions or next control word address. Okay, and now as this CMR or register, this address register is getting the value from two different sources, right? If you remember, or if we apply same principle, then we need marks in front of this register. So we have incorporated these marks, and you see marks 0th input, right? It is connected with this one, and one input is connected with this decoding table. Okay, and now so rest of this control field or control word is these are the control signals. Okay, this is going to the data part. Okay, these are nothing but select input of the marks, memories read and write, right? Register file write operations, right? These are the signals going to the data part. Okay, so now if you remember, so in the decoding state, right? So this next address is don't care, and that time you see mode field is 1. So however, for fetch, right? So the next address is 1 and the mode field is 0. So meaning that after like here, so at the very beginning, okay, at the very beginning, when we press the reset signal, that time we load the 0 value in the CMR. Okay, so that is the fetch control one, right? So we want to fetch the first instruction, right? So because of that, we are loading 0 value in the here. And in the control memory, you see we have written the fetch control word at location number 0. So we'll read we'll first read the fetch control word, and in that you see the next field is 1. So that means after fetching that control word, it is saying that fetch the next control word that is stored in location 1. Now after reading that control word, and that is for decoding. So and also mode field that time is 1. As it is 1, then the address would come from this decoding table. Now after the decoding, so here you can see IR hold the instruction. So we'll get the 6-bit opcode from that, and then we'll search that opcode in this table. If there is a match, then we'll provide the corresponding address to this port, right? And then that address would come in the control memory register, and we'll load the or we'll read the corresponding control word, okay, from this memory, and then we load this one in this register. Okay, so in this way it will work. Okay, and the component that we have here, like marks, the control memory address register, okay, and this control field, right? So all of these called the sequence. Okay, okay. So this is the way we can generate the control signal, and this approach is called the microprogram based approach. And this concept or this architecture has been borrowed from book Hamacher from chapter 5, and also it is also available in Patterson and Hennessy book at chapter appendix C. Okay, so this is the one approach. Okay, and sometimes see here the control words are very flat. So sometimes it is called also the horizontal micro programming. So here, so horizontal means all the control signals are very flat. Okay. So this is for horizontal microprogram control unit. Okay, and this is the architecture. So now we'll see the other approach to generate the control signals, and that is called the hardware-based control unit. So by parallel reasoning, so you can see here, so we have the two input AND gate here. So A and B is the input and Y is the output. Okay, and we have the truth table here, right? The approach we saw just now, right? The microprogram one, right? So there we have stored this truth table into the memory, and you see, if we get the input, let's say 1 0, right? Okay, this is the input we received, okay, in the input port, and then we can search this value in this table, and then if there is a match, then we can provide the corresponding output, okay, into the output terminal. Okay, so this is the microprogram based control unit. Now you see here the same table can be represented using this logical expression, and for that purpose we have this AND gate, right? So when we say hardware based control unit, actually we are generating this kind of circuitry. Okay, or you can think this as a nothing but we are compressing this table. We are compressing this table as a gate or some hardware. Okay, so now, okay, so if we want to generate the control signal using the hardware, then what could be the approach, right? So if you remember here, so we are trying to find out the relation between input and output, right? And that way we have written this logical expression. So now in this case, you can see here, so these are the control signals, right, or outputs, and this is the input, and also output. We have the output, that is also the input, right? So here inputs are nothing but states and the output. However, outputs are these signals, right? Now to generate the control signals, for this one, let's say I or T. So we have to look into the column value, not the row value, right? Right here. So for I or D, you can see we can write that as like I or D. So you can see, so here, so the value is 0, and we can represent, so as also we mentioned earlier, so this is nothing but a state. So let's say this is the T0 state, right? We have written here the T0 state. So when the controller is in T0 state, okay, then this I or D is 0. So we can write that value as T0 and then complement. Okay, and now you see we have the value in this row. And what is the input for this row? You see input is here the state T3, right? State T3, and then this is the this state belongs to the LW, right? So we can write that as like T3 and LW. Okay. Now, okay. So which operator we should use here? So here, so you can see this is like, I mean, here I or D would be activated when the controller is in T0 state. Also, we have to activate this I or D as 1 when controller is in third state and the instruction or opcode is L. So that means, you see, we have to put OR sign, not the AND, right? So we have to activate this signal in different scenarios, and because of that we are putting OR sign. So this is not the plus, this is the OR sign, and then we have this value here. Okay, so now here, so we can write that as similar way. So this is T6, right? And then the this is the SW. Okay, so here we are complementing the T0 because we want 0 value here. So T0 would be 1, and then if we take complement, then we have the 0 value. Okay, and in this case we need 1, and rest of the field is, you see, is a down here, right? Now similarly for jump, you can see we have a value 1 here, and rest of the time it is 0. So similar way we can write the jump, right, signals logical expression. Okay, so here the first one is uh, so all this value, right, would be 0, right? We have to write all these values, right, and then this one. So if I write only this one itself, so it would be P11 and the jump instruction, right? And for all cases it would be 0. So we have to take the complement of that value, whatever. So let's say if I want to write this one, okay. So what is the input here? So T3, and this belongs to LW. So T3 and LW complement. So in this way we have to write all this expression. Okay. Or also, like if we want to minimize, then we can minimize using the K map also. Okay, so for the time being, let's say we will write using this expression. We are not considering K map. So in this way, we can write the logical expression for all these signals. Okay, right. Now the question is like, who will generate this T state, right? Got it. So, and also this different symbols like LW, SW, right? So here also, here you can, so the question is who will generate this state and these symbols, right? Okay, so to generate the state, okay, and you see states are here, you can see states are here, T0, T1, T2, T3, right, T4. Now here you can see this T2 is repeating, right? So T2 is repeating here, here, also T3 is repeating here. Okay, why are we repeating this? Because we will generate the state using a counter, and that counter is not reconfigurable, meaning that we cannot load new value into the counter. So this state, right, would be generated using the counter, and counter would be the non-configurable. Okay, so that we see in details. Okay, so, right, so that's what it is saying. State are common in all these instructions. You see, so T0, T1, and then you can see here, right? So T2 is appearing here, T2 is also appearing here, right? And also this would be T2 and also T2. Okay, T3 you can see it is appearing here. Okay, and also T4, right? And earlier case, the sequence was unique, right? If you remember, so here, right, you see these are the unique state. You see, got it. So why things are repeating? Because we are generating this state using a counter, and counter is not configurable. Okay, okay, not configurable or not loadable. Right? Now then, what would be the counter size? So here you can see we have the maximum T4, and we have started from T0. So 4 means we need only 3 bit, right? So 3 bit counter, right? So you can see here we have the 3 bit counter. Okay. So now you can see, right? So this counter, right? Counters are generating the value, and the counter has this 3 inputs. So one is your clear signal, means if it is active, then the counter initial value would be 0, 0. Okay, and we have the incrementer, like if it is 1, then it will increment the value by 1, and this is the clock. Okay, now, so what we did, first of all, what we did here, so we have encoded this state. Okay, we have encoded this state. Okay, so this T0. So we have let's say 4 state, right? T0, T1, T2, T3, and T4. So we have 4, then we are assigning 0, 0, hello, 0, 0, 1, 0, 1, 0, and then 0, 1, 1, and 4. So as it is 3 bits, so we have other state, but we are not using it. So now you see we have encode this symbol, right, using binary domain. Okay, or you can say in between we have the, like, let's say if we have decimal system, we have this number. Okay, so this is 0, 1, 2, 3, 4, and then so this is decimal system, and then we are encoding this as binary system. Now, so this is the encoding part. Now, and we have encoded this, and we are generating this thing using the counter. Now, as we have encoded, we want to get back this P0, these symbols, right? And how can we get that? We can get that value using the decoder. If we fed this counter value to this decoder, this is the 3:2 power 3 decoder. Okay. So here you see we have these symbols. So this is the 0th output line. Similarly, this is the 7th output line. Okay, and these lines uniquely specify one symbol. So for T0, this is the line. Similarly, we have to get back the add and SW, LW symbols, right? And that will get back from the opcode, right? So in that way, you see we have here opcode that is 6 bit, and we have the decoder 6 into 2 power 6. So we'll generate here, right, this symbol, meaning that let's say if it is R type instruction, then opcode would be 0, right? All 6 zeros. Then this, let's say this is a 0th output. So that time these line would be activated. Similarly, when it would be some other value, then that corresponding line would be activated. Okay, right? Now you see these symbols are coming to the control unit, right? And we have the logical expression that we have seen here. Okay, so these are the symbols, logical expression. So in this control unit, we have this, right? So if you see in the, right, this one, right, if we want to design this circuitry for I or let's say D, right? So what could be the circuitry? So T0 is coming, right? So we'll take prime of T0, and then we have the big OR gate here. Okay, so one value would be here, and then we have AND gate, and one input would be T3, another input would be LW, and then we have another AND gate here. One input would be T6, and then other input would be SW. And these symbols would come from the decoder, and this is the I or D output. Okay, so this thing we have inside here. So that circuit that we saw, we have here for this particular line. Similarly, we can generate such circuitry for all these signals. Okay, and right. So this diagram has been borrowed from this book, Hamilton and Patterson-Hennessy. So now the question is that, like here we have this clear and increment signals, like how to control this increment and clear signal, because see we have to tell after finishing the execution of one state, right, we have to say go to the next state, then we have to specify the next state, right? So let's say to specify the next state, we need this, we have to tell the input to the counter, the clear, increment and clock. Now we have to write the logical expression for clear and increment, because you see after execution of one state, right, we have to tell go to the next state. Okay, so now we have to write the logical expression for this INCL. So how can we write that? So it would be incremented during T0. Okay, and then in the next, right, we have to fetch the instruction. That time also we have to increment. And now, okay, so we have the, we have to fetch the instruction and we have to decode, right? And then we get the corresponding instruction type. Now let's say if it is LW, right? Now LW has 3 state here, you can remember, right? T0, T1, right? T2, T3 and T4, right? So we have to increment the value. So that time it would be T2, right? And T2 is set, right? Right? Many state you can see. So T2 is set. Now, I mean the same T2. Right? Now we have to tell whose T2 it is, right? So T2 and it is LW's T2. Okay. Similarly, we have to increment for T3 and LW. Okay, you see here. Right? Now it is here. Now it will increment, and then, right? So it will reach the T4, and that time it is the last state of the LW, right? So that time also we have to, right, set. I mean, we have to set the value 0, because the 0 means it is T0. T0 nothing but it talks about the fetch the instruction. So here we have the T4 and LW. Okay, why we have written T4 LW here? Because LW has finishes or it has reaches its last state, and if it reaches its last state means it has completed its execution. Now we have to fetch the next instruction, and to fetch the next instruction we have to provide the T0 state, and if we provide this, then T0, and here we will get the 0 value here. That would tell about the T0. Right? Similarly, like for, let's say here, let's say if we consider the SW, so you can see here we have to write the T3 of SW, right? T3 and SW. Similarly for increment, right? So it would be T0, T1, and then for, let's say for SW, so T0, T1. Now T2, and who's T2? SW's T2. So we have to write, so, or T2 dot SW, right? And then, so SW has here, this is the second state, then it will reach to the third stage, and then we have to clear the content. So because of that we have written. So now you see, in this way we can write the logical expression. Okay, and so we can have that circuitry here, and then we can connect, right? Then from here. Okay, so you can see we have written this thing here. So T0, T1, T2 is LW, T3 is LW, T2, SW is T2, right? So in this way we can generate the control signal. Similarly for I or D, this is the complement, right? Okay. So in this way we can write the logical expression for all these control signals, and then we can convert them as a circuit. So the most, I mean, the structure of the circuit would be the AND gate, okay, or NOT gate, followed by a weak OR gate. Okay, right? So that would be the circuit, and here it will be the control signal. Okay. And here it will be the signal from the decoder. Okay. Or maybe from the output of the controller, right, for generating the clear and increment signals. Okay. So this would be the AND OR combination, right? So in this way, we'll generate the circuit for generating the control signals, and this approach is called the hardware-based control unit. Okay. Now we'll discuss the we'll compare the difference between single cycle and multi-cycle data path. So in the single cycle data path, you see we have no non-architectural element, and in single cycle data path the CPI is 1, because each instruction is taking at most one clock cycle. Each instruction is taking one clock cycle. Now for multi-cycle data path, we have incorporated the non-architectural element, right, such as A, B, LU out, right, then MDR, right, IR, right. These are the non-architectural element we have incorporated, right. Why have we incorporated this? Because to reduce the delay. Right? If you remember that D flip-flop things, right? So to reduce the clock period, we incorporated this temporary or non-architectural element. And here the CPI would be more than 1, because if you remember right? So LW is taking 5 clock cycle, SW is taking 4 clock cycle, right? So in that way, average CPI will be more than more. Okay. Now this is the controller's uh, step table. So here you see this is the this table is for single cycles data paths control unit. So this is nothing but truth table, right? However, in this case, so this is the state table for multi-cycle based processing. Okay. So here you can see state is involved. So this is the state table. Okay. However, here no state is involved, right? Because we are generating all the signals at a time. Okay. And so because of that, this is the truth table. Okay. And you see here, like here, the clock period for single cycle one is more. You can see, for example, let's say if this is 10 nanosecond, then if we calculate the clock period for multi-cycle one, it would be lesser. So for example, in this case, let's say it is 5 minutes. So we'll see that clock period calculation later. Okay, so this is the difference in the control table that we have. So here for single cycle one, control table is nothing but the truth table. However, for multi-cycle based processor, the control table is nothing but the state table. Okay. And here the clock period would be more in the single cycle one. However, for multi-cycle one, clock period would be shorter than the single cycle. Okay. So now let's say we'll see some problem. So now you see we have designed the processor. Now we have to find out the performance of that processor. Now, as it is a general purpose processor, then it executes only the program, and program means a set of instructions. Now that program has these characteristics. It has 25% load instruction, it has 10% stored instruction, 11% branch instruction, 2% jump instruction, and 52% archive instruction. Now we have to find out the average CPI for this. So if you remember, for load, right, it takes 5 clock cycle. For store, it takes 4 clock cycle. For branch, it takes I think 3, right? So in that way, you have to multiply that clock cycle and with this percentage. So here you can see, right? So here, so branch takes 3 clock cycle, and jump also takes 3 clock cycle. And because of that, we have added that percentage and we have put 3 clock cycle. Similarly, for store one, right? It takes 4 clock cycle, 10%. And then for arc time also it takes 4 clock cycle. So you see this 4 is for 4 clock cycle. Similarly for load instruction, right, we have 25% and that takes 5 cycle. In that way, if we add this quantity, so 4.122 would be the average CPI, right? This is the multi-cycle processor CPI for this program. However, for single cycle, the CPI would be 1. Okay. So now we want to, so after this, right, this is the CPI. And if you remember that performance calculation formula, so the execution time, right? Meaning that this is a general purpose processor and we want to execute the program and we want to find out its execution time. So program means the number of instructions that program has into the CPI, like clock per instruction. How many clock cycles is required for executing an instruction, and then the T, right? So T is the cycle time, right? It would be in second or picosecond, right? So now we have this CPI. Now, so we know the number of instructions, because if we know the program, then number of instructions also we know. Now we have to find out the T, right, for this design processor. Now we'll see that how to find this T. So here, okay, so here we have made to calculate the T, we have made few assumptions. Okay, so here in each clock cycle, right, each clock cycle involves one ALU operation or maybe one memory access or the register file, right? And each instruction is using only one stage, right? Meaning that, like here in the data path, if you remember, if we fetch the instruction and then we are storing it into the IR register, and then next clock cycle we are reading the register value, right, from the register file. So that time you see that fetch component, right, they are sitting idle. Similarly, the ALU is also sitting idle that time, right? So because of that, it is saying that each instruction using only one stage at a time. Okay. Now the assumptions are that the register file is faster than the memory. Okay, and writing into the memory is faster than the reading. So why is it so? Because if you remember when we design the memory, right? So so we have designed the memory like a right, register file. Or here in this case, it would be cache memory, right? So reading logic, if you remember, so we have multiple stages of the multiplexer, right? So if you remember in the lab, we have 1-bit register, right? And then from that register, we are getting the 32-bit data, right? So we have two levels of multiplexer, right? For reading, right? Two level of multiplexer, right? For reading. However, for writing, right? If you remember to the memory, we have only one level of decoder, right? Right. So, right. So you see here we have only one level of decoder, and here we have two level of multiplex, right? So, and this is the decoder. So in that way, this takes long time than this, and because of that, we are saying that writing to the memory is faster than reading from the memory. So we'll see this thing in details, right? I mean, when we discuss the Verilog assignment, right? Now in that way, okay. So it takes a long amount of time. Now we have two data path or two critical path in the data path that we'll see. So we'll come to this formula later. So last class we see this data path. Okay. Now in this data path, right, you see the delay calculation technique, right? So we have to find out the delay between each input and output register. So here, so at the very beginning, PC would be the input, right? Because PC's content would come via this, right, to the address of this memory, right? Now, right, and then that value would be stored in the IO, right? This is for fetch time. Now for LW, you see, so that value, right? When we'll read the value from the memory for LW cases, right, and then we'll load that value in the MDF. So you see, this is the source, right, and this is the destination, right? And for this case, right, so this one would be the destination, and then this ALU, because if you receive this output, I mean, right, so this port, right, we're getting the value from ALU out. So this would be the source for LW, and this would be the destination. Got it? And same way, right, after that, we're reading that value, right, from the register file, and we're storing in A and B register. So that time, this is the source, and this is the destination. This is the destination, this is the source. In earlier case, this is the source, and this is the destination. Now next time, so this is the source and this is the destination, because you see we are storing the value in the ALU output. So this is the one destination. Now for calculating the PC class code, right? If you remember, so PC's value is coming via this green line, right? And then it is going, and then it is bypassing the ALU register, and it is going back to the PC itself. So this is the one critical path, because you see it is the longest one, right? Right. Now other paths, their pattern is pretty similar. You see here we are reading the value from a register, and then we have the multiplexer, and then we are storing it into the next register. So here also, like, we are reading the value, and then we have the multiplexer, right? And here also we have the right value, and then we are storing it into the register A and B. Right? Here also we have multiplexer. Same way you see here, after reading the value from this register, we have the multiplexer, right? And then we have the ALU, and then we are storing the value here in this case ALU out, and here in this case PC. So now, right, so this clock to queue, if you remember clock to queue, like after applying the clock, right, the time takes to get the value into the queue, right? So that is the clock to queue that we have defined as T clock to queue, and then each marks is taking T marks delay. So the delay for this marks is T marks, right? And then the delay for reading the value from the memory is T main. Okay, and then we have to write that value into the IR register, or sometimes in the MD register. So we need setup time, because if you remember, data has to be arrived prior to the clock, right? That is the setup time. So this is the one path, and this pattern you see it is almost same. So here, so register, then marks, and then the delay, major delay component like memory, and here we have the register. Same way here you can see register, clock to queue, and then marks, and then we have the major delay component here RF, and then we are storing it here. Okay. So similar way, same things, same pattern is happening, right? Okay. So in that way, you see we have only two critical paths. So one path is this PC plus 4 calculation, right? And that we have written here. Okay, so clock to queue, and then it is coming to these marks, right? And then coming to the ALU, right? And then it is going to these marks, right? And then it is going to here another marks, right? And then we have to write that value into the PC, and the data has to arrive prior to the clock. And because of that, we're adding T setup in the clock, right? So the other path is this one, T clock to queue, and then marks, and then memory, and the T setup. And we have assumed that memory, right, is slower than the register file. So you got this idea, right? So now if you go back this, right? So this component is common for all cases, and then in the delay component that we have ALU, right, and the memory. So ALU and 2 marks, if you remember, right? And then this is the T setup, like for each register, right? So here, so each register, right, we are writing the value, and the data has to arrive prior to the clock, and because of that, we are adding setup into the clock period, right? Because we want delay in the clock period, right? The age. Right? So in that way, you see these are the critical path, right? Okay. So this is the path 1 and path 2, and from that, if we take the common part, right, this part, and then we are taking the max part. Right? Okay. So this way we can calculate the critical path, right? And that would decide the clock period. Okay. So now, so this is the formula, right? So now we want to perform the performance analysis, meaning that we want to find out the execution time of that program, right? Now, so this company XYZ, they are building the multi-cycle processor, right? Right, instead of single cycle one. For both the design, the organization plans to using 69 nanometer technology, and they have designed the registers, right, of PC, right, memory, and the register file, right. So they have designed, and they have this delay. Okay, they are in picosecond. Right? Got it. And this organization has determined logic element to have a delay table. Help the organization compare each processor execution time for the program with 100 billion instructions. So the program contains 100 billion instruction, and the program shows that behavior, right, that we have seen, right? 25% load instruction, right? So that behavior. So now we want to find out the clock time, right? Cycle time. So this is the formula, right? Clock to queue here, 30 picosecond, T max is 25, right? And then max, right? So ALU takes here 200 picosecond, memory takes 250, and then the T max, right? So in that way, you see 250 is the maximum one, and then T setup is 20. So if we add them, then the value is 350 picosecond. Okay, and this is the formula, right? So we have this many instruction, and CPI is this one, okay, and this is the cycle time. So total execution time is this one. Okay. So now, if you remember, okay, so here you see the TC, that is 350 picosecond. And if you remember the single cycle one, right, the clock period was 925 picosecond, right, and CPI is 1 for single cycle one. However, for multi-cycle one, you can see here clock period has been improved, right? It is 350 picosecond, and CPI is 4.12, that is for that program, right? So execution time for that program in multi-cycle processor is this one. However, for single cycle one, this is the time, execution time. So here you can see, right? So multi-cycle processor is taking more time, right? So why is it so? Because you see this part, the sequencing part. Sequencing part means this clock to queue and the setup, right? Because every time you see this in this data path, right? So this clock to queue and then setup here. Here also this clock to queue and then setup here, right? Okay. Now clock to queue and then setup here, and also right clock to queue and then setup for this PC. In that these parts are common, this component, and that takes right 50 picosecond. Okay, and that is the extra thing that we have. Okay, and because of that, the this execution time is more, right? Okay, so multi-cycle processor is less expensive because we have only one memory, and we have removed the additional ALUs, adders, right? And also in multi-cycle processor, we have only we have added 5 non-architectural elements. Okay, in that way, a multi-cycle processor is less expensive than the single cycle one. Okay, so what have we learned from this course? So this is the summary that we learned from this lecture, right? So we have seen the disadvantage of the single cycle processor, right? So here we are using more resources and clock period is more, and each instruction is taking the same amount of time that is taken by the slowest instruction. And in this lecture, we have discussed about the LW, and that is the slowest instruction. That means all the instructions are taking same amount of time that LW is taking. So we need the balanced design approach, right, that we have seen, and we have proposed multi-cycle based processor, and we have seen how to design the data path for multi-cycle processor. We have seen the control unit design technique for multi-cycle processor. We have seen two approaches, like microprogram, right, and the hardware based, right, approach. We have also seen the program performance analysis of this processor, and we have also compared the performance with the single cycle one, and we have also seen the disadvantages of this multi-cycle processor. Disadvantages meaning that you can see only one stage is busy at a instance, right? Other stages are sitting idle. So that can be improved, right, when we will discuss about the pipeline processor. Okay, so that we'll discuss in the next classes. Thank you.